Today's topic is battery storage systems for PV off-grid applications. So I'll be focusing on the battery itself in this case, not so much on the peripherals around the battery, but rather battery technologies, their advantages and disadvantages relative to each other, and basically how to treat them. So we will look at lead-acid batteries first. Then we will compare lead-acid to lithium-type batteries, and then finally we will finish off with the lithium batteries. So before we get started with the actual batteries themselves, maybe just to put everything into context a little bit of the importance of the battery in a PV off-grid system. So if we look at the total system costs, we estimate that roughly a quarter to a third is for the PV modules. Of course, this depends on whether PV is your primary energy source or whether you're using other sources like maybe a genset or maybe wind power or mains electricity as well if you're not in a completely off-grid environment. But typically in a real off-grid PV system, you have a quarter to a third of the total costs made up by PV modules. Then you have the charge controller and possibly inverter, which makes up a relatively small percentage, typically below 5% of the total system cost. If you're using inverters, it might be a little bit more, it might be around 10%, but not much more than that typically. And then you can already see the battery really makes up the lion's share of the total system cost at over a half, followed by 10% for the rest, where we include things like cables, fuses, overvoltage protection, all the other kinds of installation materials that you require to build up an off-grid system. So you see here the battery really does make up at least half of the total system costs in most cases. So this means we need to treat the battery well for the system to last a long time, and also more importantly to keep the costs down so that we don't have too much maintenance or replacement costs for the battery, where if you mistreat a battery, a lead-acid battery especially, then you can pretty much destroy it within a few weeks or at least a few months, whereas if you treat it well, even a lower quality lead-acid battery will typically last you at least 1 or 2 years. And the best lead-acid batteries will last you 10 or 20 years. So let's get started with the lead-acid batteries themselves. And before we look at how to treat the batteries, I'd like to outline what lead-acid batteries do not like. I think it helps a little bit to remember how to treat the batteries if you focus a little bit on what you know that is not good for the batteries. So the reason I have a picture here of a battery installed in a car engine bay is because, first of all, that's the most common application for lead-acid batteries today is in the automotive sector, so in cars and trucks and motorcycles. And also because that is the worst possible application or environment for a lead-acid battery. So I think it sort of sticks in your mind a little bit. So here I list 5 things that lead-acid batteries do not like, so things that we should strive to prevent or to reduce the effect of in our PV off-grid systems. So the first point is heat. Now you'll find from the better battery manufacturers, you'll find nice data sheets which have, a lot of them have charts, and they will give you a cycle life. Sometimes they will even give you a calendar life, a chemical life in terms of years. And typically, for the more, let's say, serious manufacturers, you will find a cycle life and on one axis compared to the temperature on the other axis. So this is already an indicator that the temperature will have a great effect on the life expectancy of your battery. And it's actually so bad that if you take the data sheet, you'll find that virtually all of the values are given at 20 or 25 degrees ambient temperature Celsius for lead-acid batteries. And then in these charts, if you look closely, you'll find that typically for every 10 degrees Celsius above 20 or 25 degrees Celsius, that you halve the life expectancy in terms of cyclability. So your battery might last 1,000 cycles at 25 degrees Celsius, and it will last only 500 cycles at 35 degrees Celsius. So you see that heat is, even if you otherwise treat your battery well, one of the most serious long-term effects in terms of reducing the life expectancy of a lead-acid battery. Now, when I say lead-acid, I mean all lead battery types. So that could be liquid electrolyte, it could be AGM, absorbed glass mat, it could be a gel-type battery, etc. So some people appear not to have voice, so it must mean they're not logged into the audio, because I think most people can hear me fine. So I'm afraid there's not very much I can do about that right now. So the second point after heat is lead batteries do not like high currents typically. Now there's some exceptions, which notably is the car battery. It's actually manufactured to provide high currents. But in the vast majority of cases, especially in the case of stationary batteries used in PV off-grid systems, high currents are bad for the batteries, are detrimental to the battery. And typically the higher the current that you demand from a battery, be it discharging or charging the battery, the shorter the life expectancy. Thank you very much for helping out the colleagues. Regrettably, I'm alone here, so I can't really take care of people's audio problems. I have to focus on the session, so thank you very much for writing that in the chat. So a car battery, if you look at the job a car battery has, I think it's quite obvious. Basically, it's pretty much there to start your engine, and it's there to stabilize the whole system, make sure that you always have around 12 to 14 volts. And in a truck, it might be twice that, 25, 26, 27 volts, something like that. So a car battery has the job to start the engine, which means it needs to provide a very, very high current. So typically we will see car batteries which have maybe 100 amp hours, 150, maybe 200 amp hours, which is pretty much as big as you will find in a car. And they will have to start an engine with maybe 300 amps. So that's a very, very high current for a relatively small battery. So car batteries are optimized to provide such high currents. And the way car batteries will do that is they will try to have a very dense acid. So it means that the electrolyte in lead-acid batteries, regardless of whether it's gel, AGM, or liquid electrolyte, is always a mixture of water and acid, of sulfuric acid. Some of them will have some additives to make a gel out of the electrolyte, obviously in the case of the gel batteries, but that's pretty much the most important part of the electrolyte, is this mixture of water and acid. And in order to provide such high currents, car batteries will have a lot of acid compared to the amount of water. You'll find that actually PV batteries or stationary batteries, or sometimes they are called deep cycle batteries, they will have a little bit of a different mixture for the electrolyte, and they will have more water and less acid as compared to a starter battery or a car battery. Now, again, the reason a car battery has a lot of acid is to provide high currents, because we need to reliably start the engine, even if the battery is half empty, or in winter when it's very cold outside and the battery has a reduced capacity. So that's pretty much the main job of a car battery. Now, if we look at an off-grid PV scenario, we don't have that situation. What we have is we have a relatively low current compared to the battery size, so we don't need to have so much acid. And you'll find later the acid actually has some negative effects as well. It accelerates aging of the battery. But in general, to get back to point number 2, one thing that generally batteries don't like, specifically lead-acid batteries, is excessively high currents. Then the third point, the middle point, is an unoptimized charging curve. So when I say unoptimized, it means that there's some older battery chargers or lower quality battery chargers which don't have several charging phases, which don't have a lot of features like boost charging, equalization charge. I'll focus on those later on. But those are there for a reason. I'll explain why. So if you're using a very simple charge controller or any form of charger, which does not have those charging phases, then typically that means a reduced life expectancy for the battery. Now, two really bad things you can do is overcharging a lead acid battery. In the case of an open lead acid batteries, if you overcharge it a little bit, then it will simply start gassing. It looks like it's boiling. It doesn't actually necessarily get very hot. It depends on how much you overcharge it. But basically the water part of the electrolyte is splitting up into oxygen and hydrogen. And that is released as a gas. So that's what you will see. You can even hear it actually when a battery is gassing when it's being overcharged. So that's typically not good. It is okay, and it's actually important for a certain period of time, but if you were to do that every day, then your battery would simply be dry at some point, and if you don't refill electrolyte, then it will die basically. In the case of an AGM or gel battery, these are both battery types which are closed, so where you cannot refill electrolyte. In those cases, the battery will simply be dead, so there's nothing you can do about that. The second last point is deep cycles. Or sorry, there's one more thing I wanted to mention. It says under unoptimized charging curve, it says insufficient charge also. So what we mean by that is if you keep the battery voltage too low, that is definitely a way to destroy your battery very quickly. So for example, if your car battery is discharged and you leave it standing for several days or maybe even several weeks, that is one of the worst things you could do. If you cannot avoid it at some point that a battery does get discharged too much, make sure that you recharge it as quickly as you possibly can. Because every hour, every day you leave it discharged will literally destroy the battery day by day. So the second last point is the deep cycles. So the deeper you discharge a lead acid battery, the worse it is for the battery and the shorter the life expectancy. So what does that mean? Well, it means that if we're using these batteries in an off-grid PV scenario where we want to have a long life expectancy for the battery, and we don't need to take care of such consideration as weight, for example, which is obviously an important factor in the car as well. You can't have 200 kilos of batteries in a car. That's not in a gas-powered car. Yeah, okay, the microphone is off again. Thank you very much. So in this case, for PV systems, we need to make sure that we do not cycle the battery too deeply. So it means that we do not discharge the battery too far to preserve its lifetime. And then the last point is the low voltages, especially for long periods of time. I've already touched on that. Avoid low battery voltages at all costs. So what is a low battery voltage for a 12-volt battery? Low battery voltage actually already starts at 12 volts. 11 volts is definitely a low battery voltage, and 10 volts is already very low. So you can do that. You can do that for several hours. But if you do that every day, or if you do that for many days, or even weeks or months, then your battery will die very quickly. So this is to get the negative things out of the way first. So these are the 5 points you need to keep in mind for what lead-based batteries do not like. So things that will destroy your battery basically, or at least shorten their lifetime. So I've already mentioned some of the differences between car batteries and stationary or solar batteries. I'd like to outline a few more points here. So if we look on the left, we have starter batteries, which is our car batteries that we're used to in our vehicles. And on the right-hand side, we have solar or synonymous to that, deep cycle batteries. So don't take the word deep cycle for its literal meaning. A deep cycle lead-based battery does not mean you're allowed to discharge it completely and leave it discharged, or to discharge it completely every day. What it does actually mean is that these cycles are made for a different application, which is typically an application with low currents and where you need a lot of battery capacity, and the car battery is the exact opposite. You have very high current, but as soon as the engine is running, it's recharging the battery, so you don't need so much capacity in the battery. The battery is basically just a small buffer to start your engine and to keep everything running smoothly and to make sure your light's working even if your engine's off pretty much. So let's look at the left. Let's look at the car, the starter batteries. So these are the jobs they have to fulfill in their life in a car. They have a high current during discharge. So when you're starting your engine, you're asking a very high current from a relatively small battery. Then we have high current charging as well, because typically cars are designed so that even if I think the average commute in Europe is I think even less than 10 kilometers or like 15 or something like that. So basically a very short distance. So cars need to be designed so that even if you drive to work only 10 kilometers every day, that the battery is always recharged in that time. So if you have a short time to recharge your battery, you need to have a high current because you need to get a lot of energy into the battery in a short time. So this means we have high current charging to make sure your battery is ready to go even after a short distance of driving. Then we have shallow cycles, the third point on the left. So this means we don't discharge the battery very deeply. In fact, most of the time, a car battery will only be discharged by about 10%. In normal cycles, sometimes you leave the car standing for a couple of weeks. It might be more than that. But in a normal day-to-day scenario, discharging your battery, maybe 10% is more or less normal. The second last point on the left is that we need to have a relatively lightweight construction. Especially today, cars are becoming heavier. In fact, some of them are becoming lighter again now because a lot of different materials are being used today. But if you look back into the maybe 50s, 60s, 70s, and you compare that to today, cars have gotten very heavy because of a lot of safety equipment, a lot of electronics, and heavier engines and things like that. So in order to compensate for that, at least to some extent, the manufacturers try to reduce the battery weight. Now, the main weight inside a lead battery, you guessed it, is lead, along with the electrolyte, so the liquid that's inside. Now, the liquid is quite cheap. Electrolyte is easy to be had in pretty much every country and quite cheap, but lead is expensive. In fact, in the last 2 or 3 years, we've had very significant increases in prices of lead. So battery manufacturers try, and this ties into the last point as well, try to reduce the cost of the battery and the weight at the same time by reducing the amount of lead inside. So these are the properties of a car battery. So now let's look at the right-hand side for the solar or deep cycle batteries. You'll see a lot of the points are actually the exact opposites. So instead of a high charging, we have a low current discharging environment. So if you have, let's say, a 200 amp hour battery in a solar system, then typically you will only be discharging it with 20, 30, 40, 50 amps. Compare that to a car battery, where let's say if you have a 200 amp hour battery, you're discharging it with maybe 300 amps, so 10 times as much. So that's already a huge difference. Now the second point is the same thing, basically, just in the other direction. One was discharging, and now we have low current charging as well. The sun is typically there for several hours a day. So as opposed to the car example, we don't have 10 minutes to recharge the battery, we have hours typically. So that means we can use lower currents, which is good for the battery, and that will preserve its life. The third point is we have deeper cycles. A PV off-grid battery typically needs to cover the whole night. So obviously the sun is typically not shining during the night, so we need to provide energy during many hours during the night. Possibly, depending on the type of system you've designed, we need to provide energy even for several days, because maybe the sun isn't shining very well, we have an important application in a hospital or a mobile phone repeater station or something like that. So the batteries have a lot of storage, and we will discharge them deeper compared to a car battery. And that's also where the term deep cycle comes from. It doesn't mean we can discharge the battery by 100% every day. If we do that, we'll kill every lead acid battery. But compared to a car application where we're only discharging the battery by maybe 5 or 10% day by day, in a PV application, we'll be discharging it by 20, 30, maybe 40% day to day. And in some cases, if we have several days of no sunshine or bad weather, then we might be able to discharge such a battery by 70%. But if we do that every day, again, that will drastically reduce the life expectancy of your battery. The second last point on the right is we have a longer life expectancy as compared to a car battery. If we were to use a car battery in a solar system instead of a real deep cycle or stationary solar battery, then all other things being equal, the battery would last less long if it was a car battery, because this denser acid, this larger amount of acid compared to the water and the electrolyte, well, what it does is obviously it's there to provide the high current to start an engine in a car. But the negative side is that this acid, the more acid we have in this mixture of electrolyte, the more aggressively it will attack the lead plates. So basically what happens after weeks, months, and years is the acid is slowly eating away at the lead inside the battery, and this is an irreversible damage. So that's one of the main basically reasons that lead acid batteries age over time, because the lead is basically eaten away by the electrolyte, and it starts sinking to the bottom and becomes like a gray sludge. So what does that mean? Well, the more acid we have, the quicker this process happens, so the shorter car batteries will last. But if we look at the opposite of that, a solar battery, because we don't need such high currents, we can reduce the amount of acid, and that in turn means we have a longer life expectancy. Now, not only do we have a longer life expectancy because we have less acid, but typically solar batteries have more lead as well. If we take two 100 amp hour batteries, one as a starter battery from a car and one as a solar battery, then typically the solar battery will be quite a bit heavier. And the reason it's heavier is because it has more lead inside. It's made for a longer life expectancy, it's heavier, and that will typically give it several years more lifetime as compared to a car battery. And that in turn also makes it more expensive. That's the main cost driver for batteries, is the lead part. So to recap the properties of the batteries, on the left again, the starter batteries, we have less lead inside, so it means they're lighter and cheaper. We have a more dense acid, which is the second point, so that we can provide higher currents. The third point is we have less internal resistance. That's again, to some extent because of the acid, to some extent because of the surface area of the lead plates. But basically, the less resistance you have, the more current you can take out of a battery without the battery voltage dropping too much. So car batteries are optimized for low internal resistance. Then car batteries are cheaper because of the material. We're using less less lead, and because of economies of scale. Because obviously we have billions of lead batteries used every year for vehicles. So we have a large factory base, a large quantity of production every year. So we have economies of scale. Then starter batteries, the second last point is, are available more widely for purchase. You can find them in pretty much every country on the planet because pretty much everywhere they're being used in cars and trucks. And the last point is we have a high C rating and therefore higher currents that we can take out of or put into the battery. Now, the C rating is often a point of confusion for people even in the solar industry. It's actually relatively simple. I've put up the formulas on the bottom with an example. So car batteries are actually often rated at 10C. What does that mean? Well, if we have the number before the C, then this is the formula. Let's take an example, 3C. So it means we have 3 hours times the battery capacity in amp hours. So let's take an example. We have a 12 volt 100 amp hour battery, and it is rated at 3C. Sometimes you have several ratings on a battery. You have maybe a rating for C20 or C10 or 1C, etc. So you'll typically find a capacity matched with one of these C ratings together. These two numbers need to be seen together. So what does this mean? We have a 100 amp hour battery rated at 3C. It means that the 3 is in front of the C. So it's a multiplication. So 3 hours times 100 amp hours means we can extract 300 amps from this 100 amp hour battery. So we can extract 3 times the capacity in current. So this is definitely a high current battery. As soon as we have numbers in front of the C, we're typically talking about high current applications. Now let's take the same example if we have the number behind the C, which is much more typical of a stationary solar deep cycle battery. Excuse me. So in this example, we have C20, and then instead of multiplying, we divide the two numbers. So we take the battery capacity and divide it by that number in hours. So let's take the same example. We have a 12-volt battery, 100 amp hours, but instead of being rated at 3C, it's rated at C20. So now we have to divide. So we take the capacity, divide it by 20, 5 amps. So that's the amount of current we can charge. Typically, actually, discharge is the rating that's given for this particular battery. So this is a low current battery. This is a battery which is optimized for low current applications and which will typically, not always, but typically mean it will have a higher life expectancy because it has a less dense acid. So I'm just going to go ahead for a moment and mute a mic that somebody has on. Sorry about that. Okay. So back to the presentation. So for the solar deep cycle batteries, remember we had more lead, which means they're more expensive. We have less dense acids, so that means we have a higher life expectancy, and less, what we'll see later, sulfation, which is this not only the effect of eating away the lead, but sulfation is actually results in crystals, you'll see later. We have a higher internal resistance. This is not something we want to have. This is the result of having a less dense acid. So it means that you can extract less current out of the battery, and that means we have a lower C rating. And I've already explained that it means we can take less current out of the battery. So let's look at the different types of lead batteries. We typically have 3 types, or at least 3 rough categories. We have the open type vented batteries. So those are the ones where you can actually refill distilled water, never refill electrolyte, only distilled water, because electrolyte, unless you have a real leak, never disappears out of a battery. It's the water portion which is broken up into hydrogen and oxygen and which dissipates as gas. And that's the part you need to replace. So you never replace it with electrolyte. Otherwise, your electrolyte keeps getting more and more dense. Then we have AGM, absorbent glass mat batteries. In fact, they're also liquid electrolyte, but instead of really being a liquid that you can slosh around inside, we have sort of a fiberglass material which sucks up the electrolyte like a sponge. And this means that you can actually typically use AGM batteries even on their side or upside down. It depends on the manufacturer. And then finally, we have gel batteries. Again, we have very similar electrolyte in all cases, but in this case, the manufacturer has added a substance to make the liquid electrolyte into a real gel so that it doesn't move at all. So that's really the kind of battery you can install in any possible orientation. So the first type is the open liquid electrolyte. Those are typically the cheapest. They do require some maintenance, so you need to refill them from time to time with water. They're sometimes better for hot climates, simply because these will actually evaporate the most water out of all 3 types, but they have the advantage that at least you can refill them. So the effect of heat is actually the highest here because we're losing a lot of water, but we have the possibility to add water as well. And you can actually use them, some of them, with recombination plugs. It's what you see on the bottom here. What it actually does, like I said, the gas that comes out of batteries when they're being charged above a certain voltage is actually oxygen and hydrogen, which is just water being broken up into the individual atoms. This top recombines hydrogen and oxygen and makes it back into water, and then it basically just simply drips back into the battery as water. This doesn't work 100%, so there's still some gas which is leaving the battery, but it means that you can have much longer service cycles. Typically, these batteries can only be operated upright because, again, it's a liquid electrolyte, so if you leave them on the side, they will leak typically. And of these batteries, the one with the longest life is the OPZS. So that's simply a type with tubular electrodes. So then we have the middle section, which is the AGM batteries. So these are medium cost compared to the others. They require no maintenance, so there's no way to add any water to the AGM batteries, at least the vast majority. They're often used in cyclical or traction applications. So cyclical, like for example, 1 cycle every day or 2-3 cycles per week. Traction application means for things like electric wheelchairs, carts, things like that, golf carts. A lot of them use AGM batteries. And most of these AGM batteries can be mounted in any orientation. And then finally, we have the gel batteries. So here we have the highest cost typically. Again, we have no maintenance because there's no way to add any water. These are most suitable for cold environments. So if you're working, I don't know, for example, ski stations, somewhere in the mountains, etc. These gel batteries are the least likely to crack when freezing. So they're quite good for cold temperatures. Pretty much all of them can be installed in any direction, in any orientation. Typically, they have a very low self-consumption, so if you leave them standing around fully charged, then they will discharge a little bit slower than the other counterparts. And of the gel batteries, the ones with the longest life are typically the OPZV, which is almost the same thing as the OPZS. Again, we have tubular electrodes, but in this case, obviously gel as an electrolyte. So let's look at the 3 main effects that reduce the performance of lead-type batteries. So the first one is sulfation. I've mentioned this word before. What it means is that white crystals build up on the lead plates. So those crystals are actually a result of the reaction of the sulfuric acid in the electrolyte with the lead plates themselves. So again, part of the lead is eaten up and basically ends up on the bottom of the battery. But some of this reaction process means that there's simply a layer of like a white, rough coating over the over the lead acid plates. And when the lead is covered by these crystals, that means that the performance is reduced of the batteries. So the lower the battery voltage, the more pronounced this sulfation effect is, the more serious it is. Also, the higher the acid density, so the more sulfuric acid you have inside, the more prone the battery is to this effect. So generally, car batteries are more prone to sulfation than deep cycle solar batteries. The result of this coating, basically, of crystals on the lead plates is that we have a higher internal resistance, so we can take less current out of the battery, and we have a reduced capacity of the battery. This effect is mostly reversible to a certain extent. Then in the middle, we have the stratification. What that simply means is that we have layers of electrolyte. So on the, I always forget which way around it is. I believe it's water on the bottom and electrolyte on the top because the electrolyte is heavier. Sorry, so it should be the other way around. Water on the top, electrolyte on the bottom. And what that means, obviously, if you do not have a uniform distribution of your electrolyte mixture, then of course the top of the battery will behave very differently to the bottom of the battery. So that means we have unequal aging, we have lower performance, and this typically only happens with liquid electrolyte batteries because obviously if you have a gel, then it's pretty much impossible for the water portion to split from the acid. This also increases the resistance and decreases the capacity, much like the sulfation, and it's also pretty much a reversible effect. And then the final, most long-term effect, and the one which is not reversible, is the consumption of the lead, which is basically that the lead plates are being gradually consumed by the acid. So this again decreases capacity. So this is a permanent damage. You can't really stick that sticky sludge you find on the bottom of the battery back onto the lead plate. So that's a permanent effect. So this is our typical charging curve, of Steca charge controllers or even standard battery chargers. And what we do is, like the simplest form of charger typically has only one voltage, and that's typically the float voltage. So let's say that's 14 volts. It means that your battery will always have 14 volts or less. When you're charging your battery, the voltage will go up, up, up until the level is reached of the charger. So in this case, in a simple charger, it's only float. So what we have is we have two additional forms of charging or charging phases, which are in the absorption equalization phase, and they're called equalization and boost charging. And these voltages are higher than the float voltage. Now, why would you want to? Because this is basically a controlled form of overcharging the battery, which is actually necessary for 95% of all lead-acid batteries. Why would you want to overcharge the battery to some extent? Well, there's a couple of reasons. So first of all, it's to reverse the two effects that we had before, the sulfation and the stratification. Remember, the sulfation was the crystals which are building up on the lead plates, and the stratification is the water and the acid which are coming apart and building layers inside the battery. So what happens is when we have higher voltages here, the boost or the equalization phase, is we have a controlled gassing of the battery. So because there are small bubbles which appear in the battery, which is the oxygen and the hydrogen being split apart from the water, what that means is, first of all, the sulfation, the crystals which have built up on the lead plates, they will come off because it's as if you have, let's say you paint a piece of metal, and underneath the paint there's some air, and if, for example, there's seasonal effects or something, the air expands and contracts with temperature, then at some point the paint will come off because the paint is not completely fixed to the metal surface, but because there's some air in between. That's sort of what's happening here. Is the crystal is attached to the lead, but because gas is forming underneath the crystal, between the lead and the crystal basically falls off and sinks to the bottom. So that's the desulfation. And then because this is almost like a carbonated drink, like a pop soda, it's also having like a mixing effect. So it will actually mix the electrolyte and therefore reduce stratification. So those are the two main effects for boost or equalization charge. And equalization charge, what it also does is in a 12-volt battery, you have 6 battery cells with 2 volts each. A controlled overcharging of the battery ensures that every cell has the same voltage. So that's what the actual equalization term means, is that we're equalizing the voltage of every cell in the battery. So we've looked at the detrimental effects of batteries and how they affect the batteries. Now let's look at the positive sides, how you can increase the life expectancy of lead batteries. So the first point, keep them cool. Like I said before, every 10 degrees you go up from 25 degrees Celsius, you roughly half the life expectancy. Then keep the battery near the floating voltage as long as possible. In other words, don't discharge the battery too much. If you can keep it at 14 volts or 13.8 or something like that, then it's happy for a 12-volt battery. Then typically VRLA, valve regulated lead acid, which is simply another term for the open electrolyte liquid batteries, AGM and gel batteries, which are sealed types, they all need high voltages regularly. They need the boost voltage. Most of them even need the equalization voltage. There's a little star here because you need to check with your battery manual what the highest permitted voltage is. But I recommend that you use that. What's important to know as well is that this phase here, the boost and the equalization, is only for a certain amount of time. It's typically for about 2 hours. So that's to make sure that we have these positive effects, but that we make sure that we're not losing too much water during this gassing process. Then the fourth point is do not exceed C5 or C10 currents for solar batteries. So it means that the capacity printed on the battery don't discharge or charge with more than 1/5 or 1/10 of that capacity. So in the case of a 100 amp hour battery, 1/5 is 20 amps and 1/10 is 10 amps. Avoid deep cycles, even with deep cycle batteries. I've explained that already. And the deeper the battery is discharged, the more important this desulfation process becomes later on. So it's important that you do a boost or an equalization charge after a deep discharge to make sure that we get rid of these sulfur crystals. And we do this automatically with our charge controllers. And then finally, for the liquid batteries, make sure you check the level of electrolyte regularly and refill with distilled water if there's some missing. Now, any one of these points, if any point is disregarded, then you obviously reduce the useful life of your battery, in some cases dramatically. So now let's compare lead acid with lithium batteries. I know it's a little bit much text and we don't have all that much time, but you will have access to this presentation later. We will send you a link and then you can read up later if you like. So when we compare lead batteries with lithium, obviously lead batteries are much cheaper. We find that lithium batteries are roughly 100 to 300% more expensive than lead batteries if you compare the same theoretical capacities. So if you compare a 100 amp hour 12 volt battery lead with the same in lithium, then typically lithium is 1 to 3 times more expensive. Lead batteries are much simpler. We typically don't have any electronics in lead batteries. For lithium batteries, the situation is different. We have what's called a BMS, or a battery management system, which should always be installed directly in a lithium battery. It could be external as well, but my strong recommendation is to only use lithium batteries which have an integrated BMS. Lead batteries are a little bit more tolerant against over or under voltage. If you overcharge lithium batteries or deep discharge lithium batteries, then that can have catastrophic effects. With some lithium technologies, they will simply vent, so they will expel hot gases, still something you don't want to be around for. And in the more extreme cases, with certain cobalt type batteries, you've heard the news years ago with Samsung, with the Dreamliner from Boeing. They will simply explode and go up in flames. So that can be very, very negative, of course. Whereas a lead battery, if you overcharge it, it will simply gas hydrogen and oxygen, which, if you have a very small room, can be dangerous because it's obviously explosive. But in most size rooms, you will never reach a level of hydrogen high enough to cause any problems. And if you deep discharge a lead battery, well, then it will simply die slowly. It will lose capacity. If you deep discharge a lithium battery and then recharge it, then it is actually much more prone to catching fire, exploding, or venting. For lead batteries, we need a more complex charging curve. I've shown it to you before. For lithium batteries, it's actually easier. There's just 2 phases typically. There's constant current and constant voltage phases. Lead batteries prefer higher voltages as close as possible to their float voltage. So if you need to store batteries, you need to make sure lead batteries are stored at a high voltage. Lithium batteries like to be around halfway. They like to be half full, roughly. So if you store them, so typically if you buy just naked cells, lithium cells from the manufacturers, they are delivered at 30, 40, 50% state of charge. Lead batteries are not good at temperatures above 35 degrees. Like I said, it really drastically reduces their life expectancy. There's actually many lithium chemistries which are fine up to about 50 degrees, some even higher, but then they start deteriorating as well. So you can't say that lithium batteries are good for very high temperatures either, but in a lot of countries in Africa, for example, or around the equator, where you have ambient temperatures around 35, maybe 40 degrees, yes, then typically lithium batteries are the better choice, and they will last much longer than lead. Lead batteries are usable below 0 degrees. Lithium batteries typically are not. There are a few exceptions, but the majority of lithium batteries are not allowed to be charged under 0 degrees Celsius. Most of them can still be discharged with a reduced current, but they cannot be charged under 0 degrees Celsius. So it's something to keep in mind. Lead batteries are heavier and bulkier, so for the same capacity, you need a much heavier and bigger lead battery as compared to a lithium battery. Typically, we have a much shorter life expectancy for lead batteries compared to a, let's say, medium quality lithium battery. Lead batteries are easy to source and very easy to recycle. A lot of battery manufacturers pride themselves in saying that lead batteries are some of the best recycled products on the planet, because a lot of companies or a lot of factories have specialized in recycling them under more or less good conditions. Of course, there's very bad recycling methods where it's done by hand, where the acid is pretty much discarded in the environment and the lead is smelted by hand, so that's not very pretty, but it still results in a very high level of recycling for those batteries. While lithium batteries appear to be more environmentally friendly at first because they don't include heavy metals typically, such as lead, they're actually much more difficult to recycle and sometimes contain rare earths or cobalt, which is difficult to source and comes from, let's say, questionable mining practices. So you can't really say that lithium batteries are much more environmentally friendly, maybe a little more in the case of lithium iron phosphate, but we still have a lot of work to do with the recycling. So that was the comparison. Now let's look at the lithium batteries themselves. So let's look at the properties of a good lithium battery. So we need to start off at the cell level, because typically, not typically, virtually always, lithium batteries are actually made up of many small cells such as these. So you've all heard of Tesla batteries, where you have literally thousands of these very small laptop-sized cells. They're typically 18650. What that means is 18 millimeters times 650 millimeters. That's a standard size. So they are typically used in laptops, in electric cars, in stationary lithium batteries, that kind of thing. There's some other shapes as well. There's larger prismatic cells as well. But let's focus on what each of these cells should be able to do. So I'm focusing on two chemistries. We don't have the time to go into more than that. There's got to be at least 10, 15 lithium chemistries. So a lithium battery is not a lithium battery. There's so many different types of lithium batteries, and they are much more different than the difference between a AGM or a gel battery, for example, in the lead battery types. So let's focus on these two, because they are the primary chemistries that you will encounter for stationary PV systems or for even grid-connected storage. So the first one is the lithium iron phosphate battery, in short form LFP. Now, this is arguably the safest of the lithium chemistries. It's one of the least likely to explode or catch fire, which doesn't mean it's safe. I strongly disagree when people say it's an inherently safe technology. If you short circuit a cell, there's so much heat produced that you can still put everything on fire, but at least it won't explode, at least in the majority of cases. And still there will be toxic gases emitted, etc. So it's still not very pretty. But of the lithium batteries, it's arguably the safest one. We have a long cycle life of over 10 years, typically, if it's a well-built cell. So the chemical stability is quite high over time. We have a relatively low energy density, that we can still store much more energy than an equivalent lead battery. but it's relatively lower compared to the other types of lithium chemistries. We have a relatively low availability of high-quality cells. The reason is that most of the electric vehicle sector is buying different cells. Most of them are not buying LFP, apart from China, which has a very large electric vehicle industry. They do a lot with LFP, but most of the European, American, etc. manufacturers choose other battery types, notably Tesla, which does not use LFP either. So it means the market, again, just like for lead batteries, is very much focused on vehicles. So because this is a little bit more of a niche market, it means we have less cell availability. And typically it's 3.2 volts per cell. Then we have this other chemistry, which is the NMC, we call it. It's between these two, I think 90 to 95% of the batteries for PV installations or for stationary installations are one of these two chemistries. So this one is reasonably safe. It's less safe than LFP, but it's definitely a lot safer than what you have in your mobile phone, for example, which is pretty much the unsafest type of lithium chemistry, most prone to explosion and fire. We have a variable cycle life, and this is interesting because you can change the properties of the cell. You can, for example, change the chemistry so that you can use more current, or you can change the chemistry so that you have a longer life expectancy. So you can play with the chemistry for different applications. That's why this NMC cell is used a lot in electric vehicles, but you can still use it for stationary applications with a slightly different chemical formula. Then we have a higher energy density, so we can store more energy per volume as compared to the LFP batteries. And we have a better availability of high-quality cells. So again, a lot of electric vehicle manufacturers are using NMC, so that means that millions, if not billions, of cells are being produced, which have a very high level of quality, which we can also use for, at least some of them, for off-grid applications. Now, if you are sourcing lithium batteries, then make sure the cells are only from reputable manufacturers. This does not exclude Chinese manufacturers. In fact, there's very many very good Chinese manufacturers, but there's a lot of other factories like Sony, Samsung, etc., which manufacture Panasonic, which make very good cells. Avoid lithium cobalt cells. That's what you have in your mobile phone with a very high probability, or in your laptop. You know from your phone and your laptop, they only last about 2, 3, maybe maximum 4 years, and they are the most unsafe type of lithium battery. The reason they're used in phones and laptops is because they have the highest energy density. So you can store the most energy in a small room, which is of course important for portable electronics, but that shouldn't be your focus for a solar system. Treat all of these cells with the utmost respect. Don't leave anything lying around in the open. If you short circuit them, then they will go all over the place. So be very careful, please. And if you don't have experience, then never build your own packs, but buy finished lithium battery packs. And then this sort of depends on the manufacturer, but typically these smaller cells are to be preferred over the larger rectangular cells, because these tend to be manufactured at a higher quality level. So we've looked at the two most important lithium chemistries for the cells. Now let's look at the battery management system. Now this is a really important part of your lithium battery. So it's, I think if you get a cell with the right chemistry and from a reputable manufacturer, you should be fine. The BMS is actually the part where you need to pay more attention, in my opinion. Because this is basically the part which actively ensures that your battery pack is safe at all times and that your battery pack has the best possible life expectancy. So there's two main types of battery management systems. The first one is passive and the second one is active. So let's look at the passive one, which represents the majority of the market. Like if you look at like Pylon Tech, BYD, and many others, they will have a passive BMS system. So basically, A passive BMS will simply disconnect your battery when it's in any unsafe condition, or it will try to rectify the situation by eliminating energy. So for example, if one of the cells is too high in voltage, then it will try to reduce the voltage of that cell by what's called shunting energy, which simply means wasting energy as heat to make sure that that one cell of the lithium battery pack is brought back down to a safe level. So passive BMS systems are the cheaper alternative. They are usually what's called top balancing, which means that when the battery pack is full, that's when they try to balance each cell so that they all have the same voltage. It is the less efficient alternative of these two because, of course, to balance the cells, we're wasting energy. We're eliminating energy as heat. So, of course, that must be less efficient than any type of cell balancing which is happening, which is not purely by making heat. This is typically the more compact and the more common type of BMS used in residential or commercial applications. Then there's the active BMS, which is the higher end one, which is more costly and more complex. And then instead of getting rid of energy by wasting it as heat when the cells are full, they can actually take energy from a cell which is too full and bring that energy over to a cell which is not full enough. So we're actually taking energy from one cell and giving it to a cell which needs it. So this means that we increase the efficiency during balancing. It also means, though, that we have much more complex electronics, which means that we have a larger BMS, and therefore it is a less common BMS, because this doesn't make it safer. The safety of the BMS really depends on the manufacturer, on the software, and on the hardware used. You can't say that the active BMS is safer than a passive one. So when you're choosing a lithium battery for an off-grid application, or for any application for that matter, make sure that the BMS covers at least these 4 points. This is like an absolute minimum of what the battery management system must be able to do. The first one is cell balancing. So it needs to make sure that all of the cells are continuously kept at the same voltage, at least once every cycle, or possibly all the time. So this is important because if you don't do this, then at some point one cell voltage will be too high, and then the pack, if it's a safe pack, the BMS will simply shut down and say, okay, over voltage on one cell, and there's nothing much you can do about it. Then you need preferably redundant overcharge or under discharge protection to disconnect the battery whenever you're in a dangerous state, basically. We need some form of overcurrent protection and some temperature monitoring. You don't necessarily need to monitor every cell, but some cells should be monitored to make sure that the pack is not running too hot. Now, if you do need communication with your battery management system, then we have the Steca extender series of inverter chargers, which have an XCOM CAN accessory, so you can connect to that. So this is more as a reference to you. I'm not going to do too much explaining here. It's to give you a rough indication of how you should set up your charge controller or your charger, depending on the battery type that you're using. And then finally, I'd just like to summarize which devices are most suited for charging lithium batteries from Steca. So I think there's one important thing to mention. When you're buying a lithium battery, make sure that it does not need to communicate to the outside. So some batteries, for example, have a CAN communication, and they will only function if you communicate regularly with the battery. If you don't communicate, it will shut off after several seconds or several minutes. So because all except for the extender do not have CAN communication of our devices, it means these types of batteries would not be suitable for using in an off-grid system. So right now we have compatibility tested with the Solarix PLI with PylonTech batteries, for example, and with German Solar as well. We are in talks with BYD for compatibility. So at the moment, I think the most common or easy to find battery you can source to use with our charge controllers would be those from PylonTech. So generally, all of these charge controllers or inverter chargers can be used with lithium batteries because they fulfill the minimum requirements, which means you can deactivate temperature compensation and that you have enough control over the charging parameters to charge a lithium battery accurately according to these settings, which I have had on the previous slide, which you can look up later. There's two exceptions. One is the extender, which is particularly well suited because it can really communicate with the battery. So you can even use battery types which require communication. And the 6000M is also particularly suitable for lithium because even though it doesn't have a communication to the battery, it gives you much more control over the charging parameters. You might remember that I mentioned in the beginning that you are not allowed to charge lithium batteries under 0 degrees Celsius. So for example, with the MPPT 6000M, that's the only charge controller where you can really set temperature limits. You can tell it to stop charging below 0 degrees or above 60 degrees, etc. So if you're using lithium batteries, the first choice would be either a Tarom MPPT 6000M as a charge controller and or extender as an inverter. And then all of the other ones work without communication, but still give you enough control so that you can charge and discharge lithium batteries reliably.